China builds the largest oil tankers on the planet, and most people have no idea how they do it. These ships carry up to 4 million barrels of crude oil in a single fans. Voyage. That's enough oil to fuel every car in the United States for nearly 4 days straight. You heard that right. One ship, 4 days of American fuel demand, crossing the ocean on a single load. These aren't just big boats. They are floating steel cities, over 1,000 feet long, assembled from thousands of prefabricated pieces with a precision that would embarrass most construction projects on land. And China builds them faster, cheaper, and at a greater scale than any other nation on Earth. What you're about to see isn't just shipbuilding. It's the story of an industrial machine so powerful, so vertically integrated, and so precisely engineered that it has quietly placed China at the center of global energy and trade. And it all starts with something you'd never expect: a single steel plate. The scale of the machine. You've seen big ships before container vessels stacked like floating cities, cruise liners packed with thousands of passengers, cargo ships stretching across the horizon. But the moment you come face to face with a very large crude carrier, everything you thought counted as big starts to feel small, because what you're looking at isn't just a ship. It's a structure something closer to a moving skyscraper, laid on its side and pushed into the open ocean. A VLCC stretches over 1,000 feet from end to end. When fully loaded, it sinks nearly 100 feet into the water, displacing more mass than most man-made structures ever will. And then come the ULCCs, even larger, carrying up to 4 million barrels of crude oil in a single journey. To move that same volume by road, you'd need more than 14,000 tanker trucks lined up back to back, stretching for hundreds of miles across highways. You heard that right. One ship replaces an entire moving network of trucks. But this is where the scale stops being impressive and starts becoming dangerous. Because the ocean doesn't care how big your ship is. Waves in the North Atlantic can rise with enough force to twist steel. A fully loaded hull experiences constant internal stress as millions of barrels of liquid shift with the motion of the sea. Every inch of the structure is under pressure, bending, flexing, resisting forces that never stop. One weak weld, one miscalculation. That's all it takes. And it's not just about surviving one storm. It's about surviving decades of them. For 25 years, these ships cross oceans non-stop, carrying volatile cargo through some of the harshest environments on Earth. Every plate, every joint, every weld has to perform perfectly, not once, but millions of times. And yet, somehow, China builds these giants faster than anyone else on Earth. A vessel this size, something that looks impossible to even assemble, goes from raw steel to open water in under 2 years. In some cases, even less. But that kind of speed doesn't come from working harder. It comes from building differently. And that difference begins long before the ship ever takes shape. China's shipbuilding empire. You might expect the country that builds most of the world's largest ships to be impossible to ignore. But that's not how this story unfolds. Because while these massive oil tankers cross every major ocean, the system producing them operates mostly out of sight, vast, quiet, and incredibly efficient. Step inside China's coastline, and you start to see it. Shipyards that stretch for miles, dry docks carved into the land like artificial canyons, cranes towering so high they fade into the haze. This is where companies like China State Shipbuilding Corporation and COSCO Shipping Heavy Industry operate not as isolated businesses, but as parts of something much bigger. At first glance, it looks like scale is the advantage. More workers, bigger yards, more ships. But that's not what actually sets China apart. Because other countries build ships too. South Korea, Japan. They're experienced, precise, and highly competitive. On paper, they shouldn't fall behind, but they are. And the reason isn't just what happens inside the shipyard, it's everything surrounding it. China didn't treat shipbuilding like a normal industry. It treated it like infrastructure. Land was allocated, financing was aligned, supply chains were built around it. Entire industrial zones were designed to serve one purpose: to produce ships faster, cheaper, and at a scale no competitor could match. And it worked. Today, more than half of the world's commercial ships by tonnage are built in China. In some categories, that dominance climbs even higher. When a shipping company needs a new oil tanker, the decision increasingly points in one direction not because of preference, but because the numbers leave little room for alternatives. But here's where the tension builds. This dominance didn't just create capacity, it created momentum. The more ships China builds, the more orders it attracts. The more orders it attracts, the more it expands. And the more it expands, the harder it becomes for anyone else to catch up. And it wasn't just shipyards that grew. An entire industrial system grew around them. And at the center of that system, before any ship takes shape, is something far more fundamental. Steel. Before the ship, before a single weld is struck, before a single block takes shape, before any of the engineering marvels you're about to see become possible, there is steel. Enormous quantities of it. A single VLCC requires roughly 55,000 tons of steel plate. That's more steel than went into the Eiffel Tower, multiplied by nearly 7 times. You heard that right. One oil tanker consumes the steel equivalent of 7 Eiffel Towers. And in China, that steel doesn't travel far. This is one of the most underappreciated advantages in the entire Chinese shipbuilding story. The steel mills and the shipyards are part of the same national industrial chain. When a yard places an order, the steel arrives quickly, cheaply, and to exact specification because the supplier isn't a separate company on the other side of the world. It's a state-aligned producer operating inside the same economic ecosystem. The plates arrive at the yard in standard dimensions and are immediately fed into cutting and forming operations. Computer-controlled plasma cutters slice each plate to within fractions of an inch of the required shape. Hydraulic presses curve flat steel into the compound shapes demanded by the hull's geometry. Every piece is labeled, cataloged, and assigned to a specific block in the assembly sequence before it ever leaves the fabrication shed. But this is where the tension begins to build. Steel at this scale is unforgiving. A plate that's been cut a quarter of an inch off spec doesn't just waste material, it introduces a misalignment that compounds across every subsequent weld, every adjoining block, every structural joint downstream. By the time that error reaches final assembly, it can mean a hull section that doesn't seat correctly, stress concentrations in the wrong places, and repair work that costs far more in time than the original mistake. This is why precision at the steel stage isn't just about quality, it's about survival further down the line. The steel gets it right. And then it moves to the step that transformed modern shipbuilding forever, the modular construction method. Here's something that will change the way you think about how ships are built. A VLCC is not assembled the way you'd build a boat in a garage keel first, then ribs, then hull, layer by layer from the bottom up. That method, used for centuries, is far too slow and far too dependent on sequential steps. You cannot start the interior while the hull is still being formed. You cannot run piping before the structure exists. Every phase blocks the next. China and the broader modern shipbuilding industry, it now leads, threw that model out. Instead, a supertanker is built the way a Boeing assembly line builds a jet, in massive prefabricated modules, constructed simultaneously in different parts of the yard, then brought together for final assembly. These modules, called blocks, can weigh anywhere from 300 to over 600 tons each. Each block is a complete structural section of the ship, fully outfitted with internal framing, piping runs, electrical conduits, and insulation before it ever reaches the dry dock. A single VLCC is broken into over 100 of these blocks. They are built in parallel, across multiple fabrication halls, by specialized teams working on their section, while every other section is being built at the same time. The payoff of this system is staggering. Total construction time collapses. Labor efficiency multiplies. And because each block is completed and inspected before assembly, defects are caught and corrected at the module level, not after the entire hull has been welded together. But here's where the tension lives. Parallel construction only works if every block arrives at final assembly with tolerances that match the blocks it will be joined to. We're talking about structures the size of apartment buildings, fabricated weeks apart, in different sheds, by different teams, and they have to fit together within millimeters. Getting that right requires something no human welder working alone could ever deliver consistently enough. And that's exactly where robotic welding enters the picture. Robotic welding at scale welding A VLCC by hand would be like trying to paint a highway with a single brush. The math alone makes it almost absurd. A single supertanker contains hundreds of miles of weld seams connecting thousands of steel plates across a hull that has to perform flawlessly under pressures most structures on Earth never face. Human welders are skilled, but human welders tire, vary, and slow down. At this scale, that's not acceptable. China's major shipyards deploy automated welding systems that operate with a consistency no human team can match. Robotic arms track pre-programmed seam paths across steel panels, maintaining arc temperature, travel speed, and wire feed rate within tolerances so tight that the resulting joints are structurally superior to most hand-welded equivalents. In flat panel lines where large hull sections are assembled horizontally before being lifted into position, automation handles the majority of the primary welds, and the speed is something else entirely. An automated welding line can process steel panel sections in a fraction of the time a manual crew would require, running continuously across multiple shifts without degradation in quality. For a country trying to build supertankers faster than any competitor, this is not a luxury. It is the foundation of the entire production model. But automation creates its own tension. Robotic systems are exceptional on flat, predictable geometry. The moment the structure becomes complex, curved hull sections, tight interior spaces, joints where 3 or 4 plates meet at compound angles, the machines hand off to human specialists. And those transitions have to be managed with extreme care. Because a weld quality mismatch at the boundary between automated and manual work is exactly where fatigue cracks begin. The yards that get this right, and China's top facilities, have produced hull sections with a structural integrity that allows these ships to absorb decades of ocean punishment without failure. Every one of those welds, automated or manual, is building toward a single moment. The moment the blocks finally come together in the dry dock. The dry dock awakening. You've seen construction sites. You've seen stadiums being built, bridges being assembled, skyscrapers rising floor by floor. But nothing in civilian construction prepares you for what a supertanker dry dock looks like at full operation. It is, without exaggeration, one of the most overwhelming industrial environments on the planet. China's largest dry docks stretch over 1,300 feet long and nearly 200 feet wide, carved directly into the earth along the flat coastline, lined with concrete walls thick enough to hold back the sea. Gantry cranes ride the length of these docks on parallel rails, each one capable of lifting hundreds of tons, moving prefabricated blocks into position with a precision that defies their scale. This is where the parallel construction model delivers its payoff. Block by block, section by section, the ship materializes in the dock like a puzzle being solved in fast forward. Bow section meets mid-body. Mid-body receives the cargo tank modules. The stern block carrying the engine room, the propeller shaft housing, the rudder assembly is lowered into place last. Each joint is aligned, checked, and welded with the same standards that governed every block in fabrication. But here's where the tension peaks. A hull this size, assembled from over 100 individual blocks, carries cumulative tolerances from every stage of fabrication. If the blocks don't align within spec at final assembly, the structural calculations the engineers built the entire vessel around become unreliable. Stress doesn't distribute the way the designers intended. And on the open ocean, under full load, that matters enormously. The alignment teams work with laser measurement systems, hydraulic jacks, and a patience that borders on obsessive. Because they know that when this dock floods, and this ship floats for the first time, there is no undo button. The water rises. The hull lifts. And what was steel plates and fabrication schedules 3 months ago is now a vessel ready to carry 4 million barrels across the world's oceans. But a floating hull is only the beginning of what makes these ships extraordinary. Engineering the hull. You might assume that once the steel is welded and the ship floats, the hard engineering work is done. That assumption would be dangerously wrong. Because a VLCC doesn't just need to float, it needs to survive. And the ocean is one of the most destructive environments any engineered structure ever faces. The first layer of defense is the double hull. Every modern VLCC carries two complete steel skins, an inner hull and an outer hull, separated by a void space of several feet. This isn't just a safety regulation introduced after high-profile spills. It is a fundamental structural decision that changes how the ship handles collision, grounding, and the slow structural fatigue that comes from decades of ocean loading. If the outer hull is breached, the inner hull contains the cargo. The oil stays in the tanks. The catastrophe doesn't happen, but steel immersed in salt water corrodes at a rate that would consume an unprotected hull within years. Every internal surface of a VLCC's cargo tanks is coated with specialized epoxy systems engineered to resist both seawater intrusion and the chemical aggression of crude oil itself. Application of these coatings is one of the most labor-intensive phases of construction. Every surface, every weld seam, every corner and penetration has to be coated without gaps. Because a gap becomes a corrosion initiation point, and a corrosion point in a cargo tank is a liability that compounds with every voyage. Then there is the structural engineering of the cargo tanks themselves. A VLCC's tanks don't carry oil as one continuous liquid mass. The cargo is divided across multiple tanks with longitudinal and transverse bulkheads. This isn't just organizational. It is how the ship manages the dynamic loads of oil sloshing in a seaway, and how it maintains structural integrity when tanks are partially loaded, one of the most stress-intensive conditions a hull ever experiences. Every system connects to every other system, and powering all of it across thousands of ocean miles requires an engine that is, in its own right, a marvel of industrial engineering. Powering a floating city, imagine an engine the size of a 4-story building. Now imagine it producing close to 100,000 horsepower while turning a propeller shaft at fewer than 100 revolutions per minute. That is the propulsion heart of a VLCC, a 2-stroke slow-speed diesel engine so large that technicians walk inside it for maintenance, and so torque-dense that it can push 300,000 tons of loaded ship through the water at 15 knots. The propeller itself is a feat of hydrodynamic engineering. Spanning over 30 feet in diameter and weighing over 100 tons, it is precision cast from nickel aluminum bronze, an alloy chosen for its resistance to cavitation erosion and seawater corrosion. The blade geometry is calculated to maximize thrust efficiency at the specific hull speed and loading conditions the ship will operate in for its entire service life. A 1% improvement in propeller efficiency across the lifetime of a VLCC translates to millions of dollars in fuel savings, and fuel efficiency is not optional at this scale. A VLCC burns roughly 150 tons of fuel per day at sea speed. Over a typical 25-year service life, fuel cost dwarfs the original construction price. This is why China's yards and the naval architects they work with treat propulsion optimization as one of the highest value engineering investments in the entire build. But here's the tension that most people don't see. Slow-speed diesels of this size generate vibration harmonics that, if not properly managed, transmit through the entire hull structure and accelerate metal fatigue in ways that are nearly invisible until they become catastrophic. The engine mounts, the shaft alignment, the vibration damping systems built into the stern section, all of it has to work in concert from the moment the engine turns for the first time. Get it right? And the ship runs for 25 years without a major mechanical failure. The engineering inside the hull is extraordinary. But what truly separates China from every other shipbuilding nation isn't what's inside the ship, it's what's outside it. China's total industrial grip. Most countries that build ships buy the Tianjin components. They source the steel from one supplier, the engines from another, the electronics from a third, the coatings from a fourth. Each of those supply relationships adds cost, lead time, and logistical complexity to every single vessel. And when any one supplier delays, the entire build schedule compresses. China doesn't operate that way. What China has built deliberately, systematically, over decades is a shipbuilding ecosystem where nearly every input to a supertanker is produced domestically, often by state-aligned entities operating within the same industrial network as the yards themselves. Steel from Chinese mills, marine engines increasingly from Chinese manufacturers, coatings, pumps, valves, navigation systems, electrical components. The domestic supply chain covers an ever-growing share of everything that goes into a finished vessel. This vertical integration is the single most powerful competitive advantage in the entire industry. It means Chinese yards quote, prices that foreign competitors simply cannot match without losing money. It means delivery timelines that would be impossible if every component had to cross an ocean before it reached the fabrication shed. And it means that when the global shipping market surges, when orders flood in and every yard in the world is at capacity, Chinese yards scale faster than anyone else. Because the supply chain scales with them. And then there is financing. Chinese state banks offer shipbuilding loans at rates and terms that reflect national strategic interest, not commercial risk calculations. For a shipping company, choosing between a Chinese yard and a South Korean competitor, the financing package alone can close the decision before price or delivery is even fully discussed. South Korea and Japan are not standing still. They are technologically sophisticated, experienced, and competitive in high-specification vessels. But the combination of ecosystem control, state financing, raw scale, and continuous investment that China brings to this industry is unlike anything a purely commercial competitor can replicate. The gap isn't closing. It's widening, and what that means for the world becomes impossible to ignore. Ships that move the world here is the number that changes how you see everything you've just watched. Nearly 60% of the world's oil doesn't move through pipelines, rails, or highways. It moves across open water. And the ships carrying that weight are the same giants you've just followed, from raw steel to finished hull VLCCs and ULCCs, built at staggering scale inside China's shipyards. Think about what that really means. Every time oil leaves the Persian Gulf, every time it crosses the Atlantic from West Africa, every time it feeds refineries in Asia or Europe, it is traveling inside a vessel that was, more often than not, assembled in China. Not partially built, not assisted. Built from the first cut of steel to the final launch into open water. And that's where the story shifts. Because this isn't just about shipbuilding anymore. It means the system that keeps fuel flowing into cars, planes, and entire industrial economies depends on an infrastructure that is heavily concentrated in one place. Not scattered, not balanced. Concentrated. The ships are global, but the machine that produces them is not. But this was just the beginning. A supertanker doesn't come and go like a product on a shelf. It stays. It operates for 25 years, sometimes longer. That means every order placed today doesn't just solve a short-term demand. It locks in a long-term dependency. A single decision echoes across decades of global trade routes, energy flows, and economic stability. And the orders keep coming, because when shipping companies look at the options cost, speed, scale, the answer keeps pointing back to the same place. The same dry docks, the same cranes, the same system you've just stepped inside. China didn't arrive here by chance. It built this, deliberately, relentlessly, aligning steel, labor, automation, financing, and infrastructure into a single, coordinated force, block by block, weld by weld, ship by ship. And now, without most people ever noticing, that system sits at the center of how the world moves energy. These aren't just oil tankers crossing the ocean. They are proof that the most powerful machines in the world aren't always the ones you see moving, but the ones quietly building everything else.